So, I request Dr. Amit Kumar sir to start our presentation.
Thanks, Dr. Ravinder, and good evening, everyone, all the participants. So let me first check whether my screen is shared. Okay. Dr. Ravinder, can you please give me access to share the screen?
Yes, sir. I am giving.
Okay. So what I'm going to do today is I'm going to cover a few supervised learning algorithms. So that is the first thing. So what I will do is in very, very simple terms, I will explain how some of the algorithms work. So that's one thing. And the second thing will be, based on the feedback from many of you, what I've done is I have created a few code samples. So for each of the algorithm, how to implement that algorithm for a particular data set. So I have done that. So I will show that. Only challenge is I have done it using Python, my preferred platform. And I think at this moment that is the most popular platform used by academicians as well as industry practitioners. So I will use Python code to demonstrate how a particular data set can be used, or rather how a particular classifier or a regression algorithm can be applied on a particular data set. And using that, I will show you also for few image data. Okay, I will also show how the things work. Okay, so I will show it for normal structured data, and I will also show the same things for the image data. Okay. What I will do is at the end, I'm going to share my my code. The code is written in Google Colab. So I will be sharing that Google Colab code with every one of you, so that later on also you can refer to them, refer to those code samples. So I will do that. Okay. So let's start off. Dr. Ravinder, can you please confirm that I am audible and my screen, my PPT is visible?
Yes, sir. You are audible and your screen is visible, sir.
Okay, excellent. So let's start. The first algorithm which I'm going to start with is a very, very simple algorithm, and that's called the KNN, or the K nearest neighbor algorithm. So let's first understand the algorithm, and then we will do some further discussions. Okay. So the basic philosophy of this algorithm lies in a fact that there is an old saying called birds of the same feather flock together, right? Or in a very simple terms, if we say, if it walks like a duck, if it quacks like a duck, then it is probably a duck, right? That's what we try to apply in this algorithm. Okay. So how is it done? Say, for example, there are some training records, and the training records have got the label. Okay, like this one, there are some images here. So these ones are the non-ducks, and these are some of the ducks. Okay, so these are the information provided by the training record. Okay, now the test record tries to find out the similarity between itself. So each of the test record, it tries to compare with each of the images in the training record, and tries to see how close to the training record, each of these training records it is. Okay, so with each, say this one, then this one, then this one, all of them, it tries to compare itself, the test record. Okay, and at the end, it figures out that, okay, fine, based on my two closest neighbors. Okay, so these are my two closest neighbors, and both these neighbors are basically ducks. So it is expected that this is also a duck. Okay, so again, just to repeat, there are few training records, and the training records might be of duck or might be of some other bird. Okay, a hen or chicken or whatever. And when we try to label, or when I try to identify the label of a test record, I just compare individually with each of the elements of the training record and try to see how close or how similar I am with each of the training record. Okay, and then I decide on, and that is basically given by that value of k, that my closest neighbors, closest k neighbors, or here closest two neighbors, they are basically ducks. That means this one is also a duck. Okay, so this is the basic philosophy. Now the thing is, there are three things to be done here. First of all, the labeled record set, that means the training record set, needs to be provided, right? So the training data which has all the instances labeled, it needs to be there. That's the first thing. Second thing, there needs to be a very clear definition of the distance metric. So when I say the training record and the test record, they are close or they are similar, how do I figure that out? So I need to define a distance metric. Okay, that will signify the closeness between the test record and the different training records. So that distance metric needs to be very clearly identified. And the third one is the value of k. So how many closest neighbors or how many closest values of the training record should I compare with? So that is given as an input to the algorithm by specifying the value k. Okay, if I mention a value k is equal to say 1, that means I will just check with the closest neighbor. Whatever is the label of my closest neighbor, I will accept that label. Okay, so that is one nearest neighbor. Okay, if I take a value k is equal to 3, that means I'm going to check with 3 close neighbors, the 3 closest neighbors. And then I will take the label of each of those 3 closest neighbors, and based on whichever is the majority level, I will take that as the label of the test record. Okay, so say for example, the test records which are closest have the labels of A, and say B. Okay, so 2 of the closest neighbors have A as the label and one of them have B as the label. So in that case, the majority is A. So that A, that class or that label will be assigned to the test record. Okay, so that is the basic philosophy. So how to do it? How does the algorithm execute itself? So the first thing is for that unknown record, that means when I have a unknown test set. So there are few records in that unknown test set, right? So for each of those records, what I will do, I will compute the distance to the other training records. So for each of the training records, each instance of the training record, distance will be calculated with that particular unknown record. So we will take one test record at a time, compare it with the different training records, and then we will come up with the label based on the majority label. Okay, so that's the first thing. So identify the k nearest neighbors. So that's the second step. And third step is use the label of the nearest neighbors to determine the class level of the unknown record. So 3 steps. 1, calculate the distance between the test record, individual test record, one record at a time, with all the training records. That's first step. Second, take the closest k nearest neighbors. Okay, so the value of k, if it is defined as 4, take the 4 closest training records. Okay, third step, whatever class levels are there of those 4 records, take the majority of that and use that as the label of the test record. Okay, so this is how we do it. Before we discuss the pluses and minuses of this, or the pros and cons of this algorithm, let's try to see with an example. Okay, so okay, fine. Here is one more thing. One of the most popular metric for finding the distance is the Euclidean distance. I think many of us understand it. It's basically the distance between 2 points calculated as Euclidean distance. Like there are many other measures, like Manhattan distance is there. Then for binary data, we can also go for Hamming distance. So there are different distance measures. Like here, the most popular measure which is being used for a normal data is Euclidean distance, which is basically root over of the square difference between the coordinates. Okay, so if I have a coordinate as x1, y1 and another coordinate as x2, y2, right? So what I will do, x2 minus x1, okay, plus x1 plus y2 minus y1, okay, squared, both of them squared, and that we will take for all the elements. So if there are multiple values, say the test record has xt, yt as the coordinates, and the training records have x1, y1, x2, y2, x3, y3 like this. So for each of the points, we'll have to calculate like x1 minus xt square plus y1 minus yt square. Okay, so like this, we will have to keep on doing that summation for all the different points of the training record, and we will calculate the distance. Okay. Now let's take a look at a particular data. Okay, say for example, I have the data of a few students, and the students have been graded based on certain qualities like communication and aptitude. Okay, and there is a grade being assigned in a scale of 10. A grade is being assigned. So each of the student has been assigned a grade. Okay, say for example, the first student Karuna has a grade 2 in aptitude and a grade 5 in communication. So that person, that student Karuna, can speak well, but it's he or she is in a little low in terms of aptitude. Okay, so the class that Karuna belongs to is speaker, right? So likewise, Bhuvna aptitude level is 2 and the communication level is 6. Also belongs to the class speaker. Like this, the next one, Gaurav, has aptitude level 7 and communication level 6. Both of them bit high. So marked as leader. The class is leader. So like this, we have a bunch of students whose aptitude and communication values are being known. And there is a class also which is known. Okay. So now, what do? We can basically, if we just take it, and just mind one thing, though we call all these 3 features as predictors, all these 3, name, communication, and aptitude as predictors, and this feature class as the target variable, mind one thing, name has nothing to do in the prediction process. So basically, whatever we are going to do, we are going to do using these 2 parameters, aptitude and communication, because the name of a student has absolutely no bearing with the target variable value, right? The class level, right? There is no bearing. So what we do here, let's take, since this is a very small data set, what we will do here is we will take all the students, all but one student as the training data. Okay, so we just leave one student apart and take all of the students as a training data, and that one student we use as a test data. This is purely something I'm trying to do to keep the things simple. There is no other reason behind this. Okay, and now what I will do is, if I take all the training records, right? all these training records. I think there are 14 or 15 of them, and try to mark them on a two-dimensional, the two-dimensional plane, right? So basically, x and y axis. We just keep one particular parameter as an x-axis and the other as a y-axis, and each of the data points in the training data we mark on the two-dimensional plane. What can we see? So we will see something like this. Okay, like Karuna is being plotted to this particular point. Then when we take Bhuvna, she will be very close to Karuna. Then we take Gaurav a little apart because Gaurav has both high values of communication as well as aptitude. Like this, we keep on mapping for all the different students, the different points in the two-dimensional plane, each of the points representing one of the students. And here is how all the different students are being pointed out in the two-dimensional plane, because we just have two features here, aptitude and communication, right? Now we have the test record, which is the record of Josh, right? And this Josh, this record lies somewhere here. This asterisk, this represents Josh. Say, for example, we do not know the level of Josh. We have to figure it out. Okay, it is a label data, so we actually have the label. But say for the time being, we do not know it, and let the KNN algorithm figure out what the label should be. Okay, now what should we do? From the test record, so this is the test record, this is the record of Josh. We are going to calculate the distance of all other training records. So all of these records, we are going to calculate the distance. And how do we calculate the distance? Let's use the Euclidean distance. Because otherwise, if you just look at this one, this point is so central, it can't be actually close to any of these three groups. We cannot say otherwise, right? So now what we have to do is we'll have to calculate the distance between the test record and all the other training records, okay? And that's what we do here. We just calculate xt minus xi square and plus yt minus yi square, right? So each of them, so we start with Karuna, okay? So Josh has a value of 5 for aptitude and 4.5 for communication, right? So the distance would be 5 minus 2, so 3 square plus 4.5 minus 5, so 0.5 square. We just do the addition and then do a square root of that, and that value comes as 3.051. So this is the distance between Josh and Karuna, right? Like this, Josh and Bhuvna, the distance comes as the Euclidean distance. Again, mind it, the Euclidean distance comes as 3.354. Like this, we keep on calculating for each of the training records. We keep on calculating the Euclidean distance between Josh and the respective training record. Okay, and now if we do we do an ordering. Ordering by what? Ordering by the field distance, right? The calculated distance. If we do an ordering by this, okay, what we are going to get is the closest, the second closest, the third closest. So all those values of distances we are going to get. So what we can figure out is this distance, 1.118. That means the distance between Josh and Gauri is the lowest. So if k is equal to 1, obviously only Gauri is going to be considered, because only the closest neighbor will be the one which is going to be considered, right? So Gauri is going to be considered. Now if k is equal to 2, what will happen? We will take the next value. So Gauri as well as the second one is Sushant, right? So 1.414 is Sushant, distance between Josh and Sushant. So if 2 neighbors are considered, or the value of k is 2, then Gauri and Sushant, both of them will be considered. If we take 3 neighbors, then the third one is the one Bobby, right? So then we are going to consider Gauri, Sushant, and Bobby, all 3 of them, because those 3 are the closest to Josh in terms of Euclidean distance measured using the parameters aptitude and communication. Okay. Now mine, if the number of dimensions or the number of parameters or features increase, obviously the calculation of Euclidean distance need to be adjusted in the same way. Okay. So this is the way we do it. Now, say for example, we are doing a 1 nearest neighbor or a 1 NN, right? So if we do a 1 NN, what will be the label for Josh? The label for Josh will be the label of Gauri, which is intel. So in that case, if we go for 1 NN, we have to go with the label for Gauri, which is basically intel. We will assign the label intel, sorry, we will assign the label intel to Josh. Okay. Say for example, we go for 3 NN. Okay. So all 3, Gauri, Sushant, and Bobby. So Gauri and Bobby, they have the labels as intel, and Sushant has the label leader, right? So in that case, the majority vote will go for intel. Again, Josh will be assigned the label intel, right? Now there is a question. In case we go for a 2 NN, okay, or even if we go for 3 NN or 4 NN or 5 NN, and there is a tie, okay. So here if we go for 2 NN, there is going to be a tie, because if we go for 2 NN, the closest 2 are Gauri and Sushant. And Gauri has the label intel and Sushant has the label leader. Which one should we go by? So basically that will depend on the tie-breaking strategy that has been implemented as a part of the algorithm. Okay, and there can be different tie-breaking strategies. Like one tie-breaking strategy can be using the weights. Okay, so weights means, say for example, here there are only 2, right? So basically if we go by the weight based on distance, obviously the weight will be in favor of Gauri. So we will go with again intel, right? So if there are multiple, say there is a tie with 4 records in each of the 2 categories, right? So then we'll have to take an average weight and go by the one which wins. And one which will be the one which has a lower value, obviously, the closer ones, right? So that way we can also involve other tie-breaking strategy. Like we can also even go for a random, I mean, we just pick up any one of them. Okay, we don't apply any weightage or anything, just pick up anyone randomly, right? So that one also be a strategy. So this is how we go about the k nearest neighbor algorithm. Okay, and actually, I mean, in my lab classes, I have the students implement it. Okay, and if you actually do it yourselves also using any code, you will see you can actually compare the value which is yielded by normal Python based or R based algorithm which is implemented and the one you do it yourself. Okay, you can just compare them. Okay, so that is something you can definitely try by yourself. The philosophy behind this algorithm is just like this. You simply take one of the test records at a time, and for each test record, you calculate the distance between the test record and the training records, each of the training records. And the distance measure can be something like a Euclidean distance. And then do an ordering by the distance, pick up the top k instances, training instances, top k instances based on the value of k. So if the value of k is 1, just pick the top 1. If the value of k is 3, take the top 3, and like that. And then you just simply take the majority vote, or if there is a tiebreaker, I mean tie, then use some kind of a tie-breaking strategy. This is how K nearest neighbor algorithm can be implemented. Okay. Now, certain things like choosing the right K, there is a very common question that what value of K is the ideal value? There is no simple answer to it. Okay. Absolutely, there is no golden rule which guides that, okay, fine, this is the right value of K. This is something you have to figure out based on the type of the data, how it is performing. Basically, kind of trial and error and based on your experience, your gut feel. Okay, so there is no golden rule which can tell you that which value of K is the perfect value. Just remember one thing, and it's very trivial to say, the highest value of K, okay, is equal to the number of instances in the training record. Okay, that's the highest value of K, right? But in that case, there is a challenge. If we take that, obviously, whatever is the majority class will always be allotted as the label for the test record. Okay. And what is the lowest value of K? Obviously, lowest value of K is 1. You can take the closest neighbor and go with that. Okay. So this is how we can do it. Some of the pros and cons, it's a very easy to understand and easy to implement algorithm. Okay. It doesn't have any parameter driving it other than this input user value of K. Other than that, so it's a non-parametric in nature. Basically, it's a non-parametric in nature. It can respond to the changes in the training data very quickly, which is actually a good thing as well as a bad thing. So with the variation in training record, the prediction will also vary. Okay, so that may be a good thing, that may be a bad thing also. Okay, and it can be applied for both classification and regression problems. Actually, I'm not going to get into that, but most of the algorithms which are applicable for classification can be equally applicable for regression and vice versa. Okay. Cons, the sensitive, it's very sensitive to localized data, as I was telling, because it's trying to do, it's basically, there's a name for it actually. A name for it given to it is called, it's rote learning. It's trying to learn the training data, the nature of the training data by heart. And based on that, it is trying to predict the level of the test data, right? So it's very sensitive to the data, to the neighbors, to the immediate neighbors. Obviously, it has a high computational time because, as you can understand, for each of the training test record, it is calculating the distance with the training record, right? So obviously, the computational time is very high. It is going to struggle when the number of independent variables, basically the number of predictors, is very high, right? And again, sensitive to the scale of the data. So this is the K nearest neighbor algorithm. Let me go to the code implementation of K nearest neighbor algorithm. Okay. So first I'm going to show you the code using the structured data. Okay. And I'm using Google Colab intentionally. Just for people who do not know what Google Colab is. So basically, Google Colab is an online or basically a cloud platform using which you can do programming in machine learning as well as in deep learning. So it has a support for Python as well as R. And at the same time, it also supports some of the deep learning frameworks like TensorFlow and PyTorch. Okay, so it's extremely useful. Why is it useful? There are few reasons for it. The first and foremost reason, you do not need to install anything. Okay, and since you do not need to install anything, all the different dependent libraries, importing them, and all those hassles you don't have to take. That's one. Second thing, you do not need to have a good hardware infrastructure to do programming, because otherwise when we do programming in machine learning and more so in deep learning, even in machine learning, when we work with very high dimensional data or data sets with a very high number of instances, the resource requirement is very high. Okay, so that if you need to have, you need to have a laptop or a desktop having very high, say, RAM. Okay, so either a 8 GB or a 16 GB RAM. So that is sometimes difficult to obtain. But if you use a cloud platform, you don't have to bother about that. Somebody wrote in the chat that we can very well use Anaconda. Yeah, obviously we can use Anaconda, and that is going to implement the libraries, most of them at least. But two things. Anaconda also needs a lot of space and a lot of memory to run. That's one. Second thing, even if you install Anaconda, still there are certain libraries, specifically the deep learning libraries, which we'll have to install separately, which is not there as a part of the core Anaconda installation, right? So that way, I mean, obviously you can do a lot using Anaconda. I mean, even when I do offline programming, I do use Anaconda. But when you are in Google Colab, you get all those flexibilities. There is one more very important thing, that is in Google Colab, you can actually use either CPU or GPU or TPU. So there are three options for hardware. So say, for example, my programming can be scaled up. The performance can be improved if I use GPU. Okay, I can use parallelization, right? But if I do not have a GPU in my own laptop or computer, I cannot do that. But you can actually do that. Obviously, there are certain constraints, but you can do that to some limited scale if you use Google Colab using that GPU as a hardware option. Okay, if you go to runtime, if you go to the change runtime type, and if you select GPU from here, you can always do it. Okay, that's one thing. And again, when you don't need GPU, you want to simply switch back to CPU-based programming, you can just select that as none. Okay, that's the second advantage. Third advantage, your code is going along with you. You don't need to carry your laptop or workstation. Wherever you go, you just log into Google Colab, and your code is there with you. Okay, so that's a big advantage. You don't have to carry your laptop or workstation wherever you go. You just have your code in your Google Colab and do it. Fourth, and that's another big advantage. Like here, I'm doing the code and I'm going to share that with you. So it's basically what I can do is simply I can go to share, and I can basically share the code with you. Okay, so that's something I can definitely do. Okay, so that's not possible for normal. I mean, if you have the code in your local workstation or laptop. Okay, so for that you'll have to either download the Python notebook, or you have to take a print of the notebook in the form of a PDF, whatever way you prefer, and send it, right? But here you can just simply share it. Okay, so now let me go to the code. Let me first show you the code using structured data. Okay, so what I can do is what I've done here is simply have the two code blocks separately so that you can understand easily. Okay, so first I have kept the code block for importing the required Python libraries. Okay, so like pandas is a very important Python library. There are very important 4 libraries. Okay, first is pandas. Second, this which is for data manipulation. Second, there is a library called NumPy, which is more for crunching numbers, all the statistical mathematical operations, dealing with arrays and all those things, different things. Third, there is a library called
Sir, sorry to interrupt, sir.
Sure.
Sir, actually, code is not visible clearly. Means, can you enlarge, zoom it?
I see. 1 second. Let me try to do that. Just confirm when it is visible.
Yes, sir. It is now clearly visible. Thank you, sir.
Okay, fine. So now third one is matplotlib, which is the one for plotting the different graphs, like we talked about the box plot, histogram, scatter diagram. So all those plots can be used, and there is an advanced version of matplotlib called the C mode that is also extremely rich in terms of the graphical plots. Okay, so we can use that. And there is a fourth one, very important, which is the scikit-learn or the sklearn library, which has all the functionalities related to machine learning, as well as the functionalities related to pre-processing, as well as the functionalities related to the model evaluation. So models, all the algorithms, the pre-processing related functionalities, evaluation related functionalities, plus there are plenty more. Okay, so all those can be imported just by the simple command import pandas as PD or import numpy as NP. And again, I don't want to get into detail. This PD or NP, all these are called alias. That means it's basically a short name. So whenever you need to do a function call of pandas, instead of calling it like pandas dot so and so, you can just write it as PD dot so and so, right? So it is basically a short form or aliasing, right? So what I've done is I have imported all the necessary Python libraries in one place. Okay, and how can I run this code? Simply by clicking on this arrow, or I can do a press control and enter at the same time. So both cases, the particular selected code block is going to be executed, right? So once that is being done, the first time it's going to take a little bit of time because it's going to set up the connection and then run the code. Okay. So once I do that, the next thing I'm going to do is I have to import the data. Now, this is a two-prong approach. First of all, you need to import the data to the Google Colab. Okay, because Google Colab is a separate platform by itself. It needs to have the data unloaded or uploaded in it, right? So for that, what we can do is we can use the google.colab library, and there is a function, there is a module called drive. So we can use that drive module and use the drive.mount to mount the Google Drive. So I can just use my Google Drive from here. So I have a folder here named, one second, I'm just going to pick up. So I have a folder in my Google Drive named IGTUW, right? And in that folder, I have a few CSV files, okay? So all those required CSV files I have kept in that particular Google Drive. So what I do is I just upload the file appendicitis.csv. So there is a file appendicitis.csv. So I upload it from here. Okay. So I simply run that code. And after that, there is a pandas command read underscore CSV. This is to read that CSV file and create the data frame object. So the object in Python, which is used to onboard or to upload the data, is known as data frame object. So what this particular command pd.readCSV is going to do is it is going to take that CSV file data and create a data frame object data. I have named it as data, and load all the data from the CSV file into it. And this particular function, data.head, it will show the top 5 rows of the data set. Okay, so there are commands in Python, commands in pandas, head, dot head, or dot tail. Dot head returns me the top 5 rows, dot tail returns me the bottom 5 rows. Okay, so what I am trying to do here is simply I'm trying to see the top few rows. So when I execute, it will basically take the permission. Okay, so for that permission, I will need to go to my respective, I need to sign into my respective Google account. So I need to copy this particular string and I need to put it here. This is my authorization code. And when I press enter, now my drive gets connected or my drive gets mounted. Okay. And once my drive gets mounted, it's going to pull up the CSV file onto Google Colab, and then it is going to create this data object or the data frame object and load the data from the CSV file into it. And when you see the top 5 rows, you can see something like this. This is basically a spreadsheet. Okay, if you just go here and pull up the data from here, you will see the similar spreadsheet. Okay, it's basically the same spreadsheet. It's taking a bit of time. So it's going to take the same spreadsheet. Okay, it's taking a bit of time. Okay, see, 81, 82, 83, like this, all the predictors, and there is a target variable. Okay, the same thing you can see here. Okay, so this is how we onload the data and create the data frame object in Python. So once that is being done, the next thing that we have to do is we have to split the data. Okay, so 2 things. One is we have to first divide the data into predictors and the training, target. Okay, so the whole data we need to divide into the predictors and the target. Okay, so that's the first thing that we do, predictors and target. Next, what we do is both predictors and target, we have to divide into 2 chunks, training and test, right? And there is a function called train underscore test underscore split, which is given by the sklearn model selection module. And we can use this to split the data set into 2 portions. One portion will be used to train the model, and the other portion will be used to evaluate the model, right? So this is how we do the, basically we do the data splitting, okay? So we do it and we run the code, and then we are actually going to look at the code for KNN classifier, okay? What I have also done here, I have actually noted the time, okay, the start time and end time for training the model and to test the model. There is a specific reason to it. I will come back a little later, okay? But there is a reason to it, okay? So how do we do it? So first of all, from the sklearn, we need to upload or onload the k nearest neighbor classifier module. So for each of the algorithm, there is a specific module. So I take that, and there is one more module to calculate the accuracy. When a particular model is being evaluated, we need to look at the accuracy. So there are different modules or different functions for that. Okay, one of them is accuracy. There is another one called confusion matrix. You can actually print the confusion matrix using that. So for the time being, let's just focus on accuracy score. Okay. So first what we do is we templatize, we create a template model for k nearest neighbor classifier. And here we set a k value of 7. So here, this value of k needs to go as a user input. I give it as 7. I could have very well given it as 3. Okay. And then what I do is I do a model fitting. How do I fit the model? I give the parameters as predictors train. So for the training, there are the predictors portion and the target train. So basically, the predictors train and the target train, both the training data, okay? And that will fit or that will train my model. So this fit function is for training my model, okay? Now, once the model is being trained, next, we have to give the test data. And what test data? The predictors test data, because it's going to generate the target test or the predictions by itself. And the predictions and the target test need to be compared to see how close the predictions are to the ground truth, right? So we do that here. So prediction is equal to KNN dot predict. The dot predict makes the predictions. Using what? Using the predictors test, right? And then I generate the accuracy score. How? The target test, that means the ground truth, and the prediction. I compare the target test and the ground truth. Okay. And that's the way I get the accuracy. And I just print the accuracy of the model. And both the time taken for the training as well as the time taken for the test is being printed. Okay. Now, when I run this code, it's going to generate it. So you see that the model accuracy is coming as 0.875. That means for 87.5% records, there has been a correct classification. That means the ground truth and prediction, the labels are matching. That's one important point to note. The second point to be noted is, see, here the time taken for training is 0.0027 seconds. Okay, so 0.0027 seconds. And the time taken for the test is 0.005 seconds. Okay, so this is one important point. See, the time taken for training is less and the time taken for test is more. Obviously, you can understand 0.005 is more than 0.002, right? You may wonder why is training taking less time, because training means we are training the model, we are building the model, right? Why is it taking more time? Why is it taking less time than testing? Where testing is basically you are applying the model on a test record and trying to get the label for it. Why is it taking less time? Okay, so this is the reason. The reason behind this is just try to understand. In essence, for KNN classification, actually there is nothing called model training, because the model training is something where you are actually building some model. Whereas in KNN classifier, what is happening is when you are getting a test record, you are comparing each of the test record with the training record and trying to find out the label. So actually every activity starts when we are getting the test records with us and we are trying to find out the label for the test record. So basically the testing is actually the place where some activities happen. Okay, this is something which is also, there is a term for this, just like rote learning, same way there is a term which is applied for KNN classifier, which is called lazy learning. It is a lazy learner. Why a lazy learner? Basically, it is not learning anything. It is simply waiting back and relaxing till the point of time it is getting the test data. Once it is getting the test data, it is comparing with each of the training records and trying to figure out the label for the training record. The test record, right? So basically, it's a lazy learner. Okay, so that's why we call a KNN classifier a rote learner, because it's trying to emulate the training record data by data, record by record. And it's also called a lazy learner because it's simply waiting back and relaxing till the time the test record comes in. Okay, so this is an important observation that you need to know. So again, I'm just going to summarize. Whenever we do any programming, any kind of data, when we get the input data and try to build a model and then try to evaluate the model, these are the standard set of steps. And you'll see when I go to the decision tree classifier, I will see most of the code remains the same, right? So the first portion is always you have to import a standard set of libraries, standard set of Python libraries, okay? Then you have to load the data and create the data frame object. Then you have to split the data into predictors and target, and then into training and testing. And last, this portion is going to be different for each of the classifiers. For each classifier, you have to create or rather instantiate or rather templatize one particular this thing model. Okay, this is my template model which I get here, and then with the training data I will have to fit the model or train the model, and then the model which has been trained or fitted I will have to apply on the test data and look at the accuracy score. Okay, and this is how we do the entire process. Okay, I hope we could understand it. I will take a pause, and if there are certain questions, maybe I think it's a logical time to take a few questions. Dr. Ravinder, if there is any question, please.
Yes, sir.
Okay.
How to unzip data on Collab?
It's not unzip, I think it's upload. So basically, this is the code you have to use to upload data in Collab. You have to keep it the best way. There are other ways also. The way generally I also do is keep it in a Google Drive, so that again, the basic objective is you can roam about and have the data on cloud, right? So you keep the data also in your Google Drive. You upload the data from the Google Drive to the Google Colab, and then you just read the data in the form of a data frame object. So this is how we work it out.
If Anaconda is already installed, can we use Collab along with that?
If what is installed?
Anaconda.
Yeah, absolutely. See, Anaconda is to do programming on your local workstation or laptop, right? It's your local setup. Okay. Whereas Google Colab is your cloud platform. Okay. So basically you can use both. I mean, like I have both of them. I have Anaconda installed in my laptop. Okay. I often use Spider also. At the same time, many a times I use Google Colab also. It's completely on my will.
Sir, can KNN be used for regression problem?
I mean, just as I told, any problem, and I'm not going to go into that, any problem which is a classification problem and vice versa. Okay, there are ways and means to do it. Okay, how good a result it will yield, that is something we need to figure out, but it can be done. Any other question?
How to import image data set which is not in Python library?
How to, same way, we can keep it in the Google Drive and import it. So when I actually executed this code, your file extension can be anything, right? So I have just imported a CSV file here. So you can do it in the when you can import a image file also. There is no restriction in that.
If the size of the data is very large and we upload it in zip form, then how to unzip it on Colab?
There are functions for doing that also. Okay, you can always do that. There are functions to do that. I don't have it here itself, but you can use standard Python library functions to unzip. There are functions, and if I'm not very wrong, I think the name of the function is unzip only. Okay, so you can use that. Again, the very good thing about using Python is you have an excellent support both in terms of the online documentation of Python. It's a very, very well done documentation. And also the community is very, very strong. So just anytime you need to do anything, you just do a Google search, you'll get tons of code and implemented codes to do it. Okay, very honestly, I also don't try to remember the functions and implementations because there is no point in doing that. Whenever I need to implement something, I can simply go do a search, get the implementation and implement it. Okay, it's so easy. And most of the things are there in the Python online documentation itself. So I just go and refer to the Python documentation, or for TensorFlow, I use the TensorFlow documentation and just do it. So it's very straightforward.
Okay, sir. Questions over, sir.
Okay, excellent. So we will now move on to the next algorithm, which is another very powerful algorithm, which is the decision tree algorithm. And there is a reason for that. Decision tree, there are the one big advantage is it yields a very good results. At the same time, for data sets of moderate dimensions, the model which is being built, and obviously from the name itself you can understand, it builds a tree-shaped model. The model which is being built is extremely interpretable. We call it interpretable. That means we can actually understand why the decision tree algorithm takes a specific decision. Okay, takes a specific inference, makes a specific inference. That can be very easily understood. Okay, because of the inherent nature of the algorithm. Okay, so the basic way the decision tree algorithm is structured is basically it has a set of nodes, and based on the nodes, it basically divides into different branches. Okay, and these nodes are basically certain features, or it might also be each of the nodes might be different. What should I say? Different compartments or different variations or different subdivisions of a feature. Okay, I mean based on a feature. We'll look at it. You will understand that. So, anyways, the objective is you need to identify in a data set which feature should be at the root node, which features should be at the subsequent nodes, and how the branching needs to happen. That is what needs to be built as a part of the decision tree algorithm. Okay, and we will look into that. Okay, just like we looked into the KNN algorithm with an example, we will also look into the decision tree algorithm. So this is what I mean: split one, then split two. So split one splits the entire data. This is not a linear data. Obviously, you can understand there is no one straight line which can divide the data. There are multiple straight lines needed, right? So you cannot use one straight line. So how does it do? First, it splits into two subdivisions. Then one subdivision it splits into two. So here the instances are quite discriminable, right? Discriminable. Then again, the other split also it makes into two split. Here, the left-hand side, all the instances belong to the same class, but the right-hand side again has a mixed. So again, you have to create one more split, and then the right-hand side can also be divided into two portions. So this way we can actually create multiple splits to segregate a whole set of instances into multiple, what should I say, splits. And each of the split is going to have almost homogeneous class values, right? This is the way we have to define the splits. What you see here is probably a too ideal view of it because it is exactly segregated. There is no mix, but in reality, there might be certain mixes. Okay, if we are able to achieve this kind of a split, obviously we are going to have a accuracy of 1, right? 100% accuracy. Now let's look at our data. Okay, the data is a very simple data. Again, it has 5 features, out of which 4 features are predictors: the CGPA, the communication, the aptitude, and the programming skill. And the target variable is a job offered or not. Okay, so basically this is the data of, again, a set of students for whom we have a set of parameters or a set of features, for which each of the students we have evaluated the student based on certain parameters, and we have got the data of the last year, say for example, of which particular student has got the job offer. Okay, so last year we had a set of similar students and they also had the different parameters. They were also graded based on the different parameters, and then each of the students, there was a particular, I mean, we know that whether they got a job offer or not, right? So same data we are going to use this year for the different students, what we have the data for the predictors. We don't have this data because the job cycle has not started yet. And we are going to use this data to kind of come up with a prediction for each of the students. Okay, and we have to assign the value of the target variable. Okay, this is what we have to do. But before that, based on the target training data, we need to come up with a tree structure. Okay. Now, how do we do that? How do we come up with the tree structure? For that, there is a bit of mathematical calculation which is done. Okay. And there are multiple ways to do it. Here, we are looking at one way, which is by using entropy. Okay. People who are familiar with entropy, I'm sure you know there is a calculation formula for entropy, which is minus P log P. So if we have a particular data set and the data set has multiple instances, okay, and the instances, there are certain class values being assigned. And if you take a frequency distribution of that, and then based on that, if you calculate the probability value, okay, so, and the probability value is being represented by P, then the entropy is basically calculated by P log P. This is the base is 2, right? P log P. Now, how do we do it? So, say for example, with this particular data set, we had 18 records, okay? And the training data, that job offered field, which is the target variable, it has two possible labels, either a yes or a no, okay? Now, let's try to figure out how many yeses are there. So 1, 2, 3, 4, 5, 6, 7. Okay. So, 8. 8 yes. So if you come here, so there are 8 number of yeses. Okay. And number of records having no, there are obviously 10. 18 minus 8, which is 10. Okay. Now, how do I calculate the PI? Obviously, 18 divided by 8 divided by 18. So that is coming as 0.44. Same way for no, the value of P will be 10 divided by 18, which is 0.56. Okay. Now we calculate the P log P. So basically minus P into, so minus 0.5 into log of 0.5. Okay. And that value is, minus 0.44 into log of 0.44. And this one will be minus 0.56 into log of 0.56. So the values are coming as 0.52 and 0.47. Okay, these are the values which are coming as. Now we have to calculate the overall value of the entropy. So the overall value will be the sum total of this. So 0.52 plus 0.47, which is 0.99. So this is the value of the entropy when I start splitting. Okay. So when I start splitting, again, I need to divide based on the number of classes. So here there are 2 classes. If you look at the target variable, there are 2 possible classes, yes and no. And here I split into 2 portions, yes and no, right? And yes, there are 8 records, no, there are 10 records. So if I calculate PI, the probability, so 8 divided by 18 is 0.44. And for no, it is 10 divided by 18, which is 0.56. And then I calculate the entropy. What is the entropy? Minus 0.44 into log of 0.44, which is coming as 0.52. And same thing, minus 0.56 into log of 0.56, which is coming as 0.47. So what is my total entropy? 0.52 plus 0.47, which is 0.99. This is my entropy, total entropy, before I start splitting the data. Okay. Now, this is my original data set entropy. Okay. And entropy basically reflects, if you are aware of it, the information theoretic interpretation of entropy is it reflects the amount of uh, variability, okay, or the amount of lack of predictability, right? So this is my entropy. Now I do a split. I now have to figure out when I start with the root node, which is going to be a root node. Is the CGPA going to be my root node? Or is the communication going to be my root node? Or is my aptitude, that is going to be the root node? Or programming skill, which is going to be my root node? I have to figure that out. So how do I do that? So I will now, for each of them, say for CGPA, okay, I will have to again take a view of the different options in CGPA. What are the different values of CGPA available? Okay, so if I go back, the CGPA can have values high, medium, and low. How many highs are there? 1, 2, 3, 4, 5, and 6. So if you just come here and look, there are 6, total 6 high. Okay. And now for this 6 high, what is the number of yes and no of the target variable? So here, high it is yes 1, high and yes 2, high and yes 3, high and yes 4, high and no 1, high and no 2. So 4 yes and 2 no. Look at it. There are 4 yes and 2 no. When I split the CG based on the CGPA, the data set based on CGPA, I have to split into 3 portions: high, medium, low. Again, when I look at high, the portion high, I can split into the target variable value yes and no. For yes, there are 4, and for no, there are 2. So I can have 2 records for yes and 2 records for no. Okay. Again, here I have to calculate the value of PI. So 4 by 6.67, 2 by 6.33. Okay. And the entropy, same P log P. I calculate the entropy. The entropy for yes is coming as 0.39. For no, it is coming as 0.53. Total entropy is coming as 0.92, just for the portion high. Okay. Now I have to go for the portion CGPA. CGPA medium. So medium, 1, 2, 3, 4, 5, and 6, and 7. So there are 7 records with medium, okay, with CGPA value of medium. And for each of them, we have to see how many yes and no. So for CGPA medium, so yes 1, medium, this is no, medium, this is no, medium yes 2, medium yes 3, medium no, medium yes 4. So 4 yes, and obviously there will be 3 no's. Okay, the same way I calculate the PI, 4 divided by 7.57 and 3 divided by 7.43. Again, we calculate the entropy, 0.46 and 0.52, and then the total entropy as 0.99. Okay, and the last one is having no, CGPA as low. Okay, CGPA as low, how many times? So this is 1, this is 2, this is 3, this is 4, this is 5. So 5 cases where CGPA value is low. So 5 cases CGPA value is low. And how many of them are yeses? So CGPA value, this is no, this is no, this is also no, this is also no, and here also this is no. So all cases CGPA value is low, job offered is no. So yes is 0 and no is 5. So what we will get is the entropy is coming as 0. Okay, because this is 0 multiple of log pi, and this is p into log of 1, which is 0, right? So we are going to have here 0. So the total entropy is coming as 0. Now, how do I calculate the overall entropy? How do I calculate for this whole CGPA thing? How do I calculate the whole overall CGPA, overall entropy? So for this, I have to do by the proportion. So 6 divided by 18 multiplied by total entropy of this portion, which is 0.92. Okay, plus 0.999. So 7 divided by 18 into 0.99. Okay, 0.99. Now, this portion is 0, so we don't have to do anything. So basically, 5 divided by, you can just do like this, 5 divided by 18 into 0, which is going to be 0 anyways. So if we do a total of this comes to 0.69. You can just check the maths yourself. This is going to definitely come as 0.69. Now, what do I have to do? I need to calculate the entropy gain or the information gain. So when I split, I calculate the total entropy after the split. So before the split, it was 0.99. After the split, it is 0.69. What is the information gain? Because that's why I have a reduced entropy. My variability has reduced. So what is my information gain? 0.99 minus 0.69, which is 0.3. This is the information gain if I go by the split CGPA. Okay. So likewise, I can also calculate for communication. What will I have to do? In that case, I will have to bank on this particular column and divide it into two portions, one for good and the other one for the bad. Okay, other one for the bad. And I will have to do a similar kind of a splitting, and based on good, based on bad, I'll have to calculate the entropy. Then I have to calculate the overall entropy, and then I have to calculate the information gain by subtracting the entropy before the split minus the entropy after the split. Okay, and here the information gain, sorry, this one, the information gain for communication is coming as 0.36, which is definitely more than 0.30. Then we do the same thing for aptitude. It is coming as 0.47. Obviously, more than CGPA or more than communication. And for programming skill, the information gain is coming as 0.04, which is very little. So almost no information gain. So obviously, what can we decide from here? The first level of split is going to happen based on the feature aptitude. Okay, based on the feature aptitude. And there is going to be two different branches. One branch which is for the aptitude high, and the other branch which is for the aptitude low. And then for each of the branches, then we have to do a similar kind of a, so here what you can see is for the low, you will see that it is always, if low, aptitude is all low, job offered is always no. So you don't have to make any split here. You can simply take this job offered is equal to no. You don't need any further split.
Welcome
so
to my
here
first
you will need
video.
to split.
Today I will
On
tell
the
you
right hand side, no more split is required. That's a very good thing. So here on this portion, which is going to have 11 records, we have to start with the calculation again. The calculation for level 2. See, there are 11 records. And the same way we have to calculate the entropy before the split. And then with each of the other features, CGPA, communication, and programming skill, we have to look at for which one the information gain is highest. And here we can see the communication is giving me the highest information split. So what do I get? In the level 1, we know that it is aptitude, right? And we know that the left hand side is we have to split. Right hand side we already had J is equal to no. Job offer is equal to no. So the left hand side, the feature we will select is basically communication. Okay, the feature will be communication. And again, there is going to be two parts. One, the communication is good, and the other one, communication is bad. So this is for high, this is for low. Okay, now communication good, if you see, in all cases, job is getting offered. So I don't have to split anymore. So I have an end here. So J is equal to yes. Here, for communication is equal to bad, again we need to split because we see both. Some cases job is offered, some cases job is not offered. So again we have to have a level 3. So this is level 1 split, this is level 2 split, and obviously there will be a level 3 split required, for which we need to figure out what feature is needed, right? And what will be my starting point? This portion. So these 4 records. Okay, so when we go next, we will start with these 4 records and we will repeat the process. But this time we will have to do it only for 2 features, CGPA and programming skills, right? And we will see that for CGPA, information gain is highest. So now what we will get is the level 3 also. So I start here, this is my start. The first portion is my aptitude. I get 2 branches, one on high, one on low. Low, already we know that job is not going to be offered. So aptitude low, no job is going to be offered. Aptitude high, again 2 branches. And in level 2, we know that the feature which has been selected is communication. Okay, communication. So communication, there can be 2 portions. The communication is good or communication is bad. If communication is good, that means aptitude is good, communication is good. Job is going to be offered automatically, right? We don't need any further split. If the communication is poor, then the level 3 is going to be based on CGPA. Okay, CGPA. And as we know, CGPA can have 3 branches. Okay, high, and then medium, and then low. Okay, high, medium, low. And see, for each of them, entropy has become 0. That means there is no more split required. So for high, the job is going to be offered. So for high, J is equal to yes. For medium and low, both of them, J is equal to no. Okay, J is equal to no. Here also, J is equal to no. So now I have built my whole decision tree. Okay, and what is the advantage? Now any test record if I get, okay, and for the test record if I have got the value, say for example, the aptitude is say for example high, the communication is say for example low, and say for example CGPA is high. Okay, so what is the path? So it will go through this path because it is high. Then the communication is low, or rather the communication is bad. Sorry, communication is bad. So it is going to go this path. And then the CGPA is high. So it is going to go this path, right? So the job is going to be offered. We can come up with the level that yes, job is going to be offered. So this is how we can build a decision tree algorithm. So this is what I was talking about. Start, aptitude, low, job is not offered. High, we'll check for the communication. Good, job will be offered. Bad, it is going to check for CGPA. If it is high, job will be offered. If it is medium or low, job will not be offered. Okay, so this is the decision tree algorithm. And this is the biggest advantage of the decision tree algorithm is it is extremely easy to understand, at least for less number of features or less dimensional, lower dimensional data sets. What we can see is a very clear path of decisions, right? So it is very, very easy to understand. Okay. So I hope you have all understood. The maths here is a little difficult, maybe as I'm going a little bit faster. But if you look back when I share the deck with you, if you look back to the calculations and try to work out the maths yourself, I'm sure it will be pretty trivial. Okay. So now some few points, the pros and cons. Again, as I told, it's very simple to understand. The flow is very simple to understand. Works well for, it's very effective for most of for most of the data. And again, it can work well for both small as well as large training data sets. This is a very, very big advantage of decision tree. Provided the variability is covered in the data sets or captured in the data sets, even for a smaller data set, training data set, the decision tree algorithm can work well. Like you could see, we had only 18 records, right? It's a very small data set, training data set. But since the variability was very well captured, obviously other advantage was the number of dimensions was very small. It's only, it's a 4-dimensional data set. I mean, there are only 4 predictors, right? So that's why it can work well with a very small data set also, training data set. And a very clear, I mean, again, the same thing. Cons, there is a possibility that it might get biased for the features having more number of levels, okay? More possible values in number of levels. There's a possibility of overfitting, getting overfitted or underfitted quite easily. And that's why if it gets overfitted or underfitted, there might be a possibility of classification errors. But again, in general, the observation is it's quite effective, an algorithm. At least for data sets, the simple data sets that we work with, it is quite effective. Computationally expensive, it might be when the number of dimensions increases. But when the number of dimensions are moderate, then it is not so computationally intensive. Okay. For larger trees, okay, obviously, when the tree size gets higher, just you have to understand, when the tree size gets higher, the number of levels also gets higher. Okay. And also the structure, the width of the tree also may get more. Okay. So that way it might get much more complex. That's why we have to use different strategies like pruning the tree and all those stuff. But it might get complex when the number of the number of features or the dimensions gets higher. Okay. One variation of decision tree, or rather, basically, it's a ensemble of multiple decision tree. It's known as random forest. Okay, it's another very effective, very powerful algorithm. Random forest, obviously, you can understand it will be much more computationally expensive, right? So this is the decision tree algorithm. Now let's go to the code. Okay. So again, when you go to the code, the first portion of the code, when I look at the Python library import, data loading, then dividing into training and test data, everything remains the same. One point that I didn't mention earlier is the parameters. When you are splitting the test and training data, the input data into training and test, there is something which is called test size, which we provide at parameters. The basic reason why we give is it helps in setting the portion of the data as the test data. So when I give 0.3, 30% of the input data gets segregated as the test data. So if there are 100 records or 100 instances in the input data set, out of 100, 30 records or 30 instances will be segregated as the test record or the test data set, and the remaining 70 records or 70 instances will be used as the training data set. Okay, that is one thing. Second thing is there is something called random state. Basically, as I mentioned, when we are picking up the training records or the test records, we use the concept of random sampling. So basically, we pick the records randomly, right? Now, the problem is if we are picking up the instances randomly, for each different picks of the training data, obviously the instances which are being picked up are going to be different, because each time we are going to come up with a different random pick. So obviously the results are going to be different. Now, when we are working on some particular research initiative, say for example, where we are trying to benchmark something, obviously we have to publish the benchmark results, right? Then if somebody wants, he or she may want to reproduce or rerun your steps and reproduce the results. So unless you fix the composition of the training data, you cannot have the results as the same. So the challenge would be every day, if I pick up a different training record, I will get a different result, and it's not going to align whatever is a published result. So that's why what we do is we mention this random state, there is a value, whatever this value you can choose yourself. What it does is it basically seeds, it picks up a seed for the random number generation and to pick up the random instances. What will happen is every time when it comes across this code, it will pick up the random same random seed, and the random data which is being picked up, the training data which is being picked up are going to be the same. Okay, so that way, every time you're going to have the same training and the same test data, and your results will be reproducible. That is one important point we need to remember. Now coming to the code for the decision tree. Just the only difference is we have taken a different classifier, decision tree classifier. Earlier, we used the k-neighbors classifier. Here we have used the decision tree classifier. Okay, and the same way I have just set a model where I have mentioned the different. Again, here also I can give a random state, and then the max depth, okay, the max number of levels, and the minimum samples leave. Okay, these are some of the parameters we can either give, or there are standard values which are also picked up. Okay, we can choose to go as we wish, and then we feed the model again the same way, just the same way, the predictor train and the target train. Okay, obviously, because you have to use the training data for training the model or fitting the model. Once the model is being fitted, the DT is the model fitted, then you apply it on the predictor's test and you get the predictions. And then you compare the predictions with the ground truth, which is the target test, and you get an accuracy, and you print the accuracy. So let me run the code. Okay, see, I get the accuracy. And now if you look at it, see, the total time needed for training is 0.002, and the total time required for test is 0.001, which is expected. Here, we are actually building a model. We are actually learning something. Okay, and that's why the training process is taking more time than the test process, or rather the vice versa. Test process is taking less time than the training process. Obviously, here the difference is very less because we are working with a very simple data. When I show you the same thing using the image data, you will see that it's going to be much more. The differences in time is going to be much more, right? But the point to be noted is the test evaluation, okay? Getting the test evaluation takes lesser time than the model fitting, okay? And that's the reason why when we go for decision tree, we call it a eager learner. It is not a lazy learner, it is an eager learner. It learns the model, or it learns from the data right at the time of training and not at the time of testing. Okay, it is a eager learner, whereas KNN was a lazy learner. Okay, this is something you need to bear in mind. Okay, most of the models that we look at, like naive Bayes, decision tree. Then when you look at SVM, obviously random forest is based on decision tree. All of these are basically eager learners. Okay, where you will see the model fitment is taking more time than actually generating the test results. Okay, so this is the decision tree algorithm and the code using the structured data that we can write for the decision tree algorithm. Now, I'm going to show you some code using the image data. So this is the structured data. Now, I will show you some things with the image data so that you get some idea. See again, using different classifiers, you can do it yourself. Okay, you can just search what is the sklearn module to implement that classifier and then just use it. I mean, the code is almost going to be the same. Sorry. But what you need to see in this case, this is a completely different data. Here, we are dealing with the unstructured data, which is the image data. Okay, here things are not as similar as we saw in case of structured data. Okay, so here also we start with importing some libraries. So what we do is we import the NumPy library, the Pandas library, the Matplotlib library, and the time library for noting the time. And then what I have done is image data. I could have very well imported from the Google Drive also. Sorry, but I have done. I have used some of the native data sets which are there in TensorFlow datasets module. Okay. I'm sorry. So I have taken a very standard data set, MNIST data set, which is a data set having handwriting data. Okay. So if I just show you, it is very much like the data set is very much like this. So say, for example, for 0, there are a lot of zeros, handwritten zeros. Okay. Then for ones, there are a lot of handwritten ones. Okay. Sorry. So like this, you have some ones, like this one, this one. So there are many number of ones. Then there are different twos. Okay. So the data set consists of samples or handwritten samples of different digits. So 0 to 9 different digits are there. Okay. So, and at the same time, it has also got for each of the image, and all these images are like this. Okay. And each of the image, there is an annotation. Okay, so there is an annotation 0 for each of these images, annotation of 1 for each of the images. So like this, for each of the images, there is an annotation. Okay, so I will first import the MNIST dataset. I'm done with the import of the MNIST dataset. Now, here I will load the MNIST dataset, and then when I load it, the good thing is it is already splitted into training and test and predictors and target variable. So if you see here, so there are 6,000 training images and 10,000 test images. And for each image, it's a black and white image. Dimensions are 28 by 28. So basically 28 pixels by 28 pixels. It's a squared image. So each pixel is like this. Okay. And if you know about images, obviously for each pixel, there is an intensity value. Okay. So that is a image data. Now, if I just look at the image as one of the images, so see here, this is the 5. If you see the image, there is also 5. And if you just look at the label, there is also 5. If I just change it, say for example, if I take it as 7, okay, so 7th or rather 8th one, okay, so if you look at it, it is going to print something different. So it is a 3. So the image is also of a 3, and the label is also coming of a 3. Okay. Now I have some pre-processings to be done. The first thing I do is I just flatten the data. It's a square image having 28 by 28 dimensions, right? Or rather 28 by 28 pixels, right? But I do a flatten of it, so I simply get 784 dimensions, right? So 784 dimensions in the predictors, okay, and in the target you will have annotation, either 0 or 1 or 2 or 3. Okay, so I have an annotation for that. And one more thing is I do a normalization. So basically, this is the standard practice for images. Okay, so I do this. Now I run a k nearest neighbor classifier. Okay, generally, let me tell you, we do not apply machine learning classifiers for image data. We either apply a feed forward neural network, a simple feed forward neural network, or since it's an image, I can also use a convolutional neural network. Okay, so either of these. So here we are using a machine learning classifier, and as you can see, the test process is going to take a long time. I'm sorry, I'm having some problem. I'm having some hiccup. So just excuse me for a moment, okay? Sorry about that. Okay, so it will continue for some time. Let it happen. So why is it taking so much time? Because again, it's a lazy learner, right? So this is a k nearest neighbor classifier. It's a lazy learner. So it's taking quite a long time for doing the test testing. Okay, so to assign labels to the test records and to give the accuracy. Okay, so let it take its own time. We will come back to the code. And for the decision tree classifier also, the same code that we used for the structured data, we will use the same code here also. And as we can see, the accuracy coming is much less. But as you can see, the training process is taking more time and the test process is taking much less time. Likewise, we have also done it for SVM classifier. Okay, we have applied the code for the SVM classifier. And for that also, I have already run it. I'm not going to run it now because as you can see, the training process is going to take a long time. And also the test process is also going to take some amount of time. But the one I have run already, you can see the 97.92% accuracy. Okay, so it's a very high accuracy that we get, and the code is relatively simple. So what I can recommend is you can refer back to the Google Colab, and let me share it with all of you. I'm just going to make it public, okay? And you can actually do it, or let me just use your email IDs, okay? And I'll share it with every one of you. So you can actually look at the code and try to run the code yourself in either Google Colab, or you can do the same thing in Anaconda. If you have got your own installation, you can do it in Anaconda. Okay, so this is the coding portion. Let me now go to the thing. So support vector machine, again, I'm not going to go into much details about it. the basic philosophy is, say, for example, I have a very linear data, linearly separable data. So I can basically separate it by a straight line, okay? But just understand one thing, I can separate by a straight line like this, or I can separate by a straight line like this, or by this. So which one is going to be the best one to segregate the data? So for that, two concepts are being used. One is the concept of support vectors. We choose certain instances of the training data as support vectors, and then we also use the other concept, which is the margin. So what do we see? We try to see for each of the straight lines, what is the distance from the straight line with the different support vectors. And say, for example, here we can have three straight lines, or in case of a multi-dimensional data, we can have three hyperplanes or more hyperplanes. So which one would I choose? The one which gives me the highest margin will be the chosen straight line or the chosen hyperplane, right? So this is how the algorithm works. In case the data is not linearly separable at a particular dimension, say for example here, it is not linearly separable. It looks like it is non-linearly. We need to come up with some non-linear decision boundary, right? So how do we do that? So what may happen is it might be non-linear, it might have a non-linear boundary at a lower dimensional feature space. But if you abstract it to a higher dimensional feature plane like this, you might see that there is a, I mean, like you, when you look from the top, it might look as a, non-linearly separable data set. Okay, but when you see from the side, it might so happen that one cluster of instances belonging to one particular class lies at one side, and the other ones lies at another side, and you can have a hyperplane in the middle to separate them out, right? So for doing that, there are certain functions which are being applied. These functions are called kernels to kind of abstract the data from a lower dimensional feature space, to a higher dimensional feature space. Okay, and there are different popular kernels being used, like the linear kernel, the polynomial kernel, the sigmoid kernel, and the RBF, Gaussian RBF kernel. Okay, but I'm not going to get into details of that because we still have the regression to cover. Let me cover regression in a bit. And what's regression? We have already seen. Classification means target variable has a, it's of type categorical, right? It's categorical in nature. Now, if the target variable is continuous in nature, or it's a numerical variable, right? Then the problem is a regression problem. Say, for example, here we have used a motivating example of student marks, okay? Now, say, for example, there are two sets of marks, the internal and the external marks, okay? And there is a professor who believes that there is some relation between the internal and the external marks, okay? That means there is some kind of a notion that if the internal marks is higher, the external marks will also be higher, and the internal marks, if it is lower, external marks is also going to be lower. So if I consider the internal marks as an independent variable, say x, and the external marks as a dependent variable, say y, I can formulate a relationship, a linear relationship between x and y. Okay, so that is the assumption. How can I validate the assumption? Simple, by plotting the data instances, the data points. Each of these student record is a data point. Okay, I plot the data point in a two-dimensional space. On one dimension, which is the x, is my internal marks. On the other side, which is my y, I have the external marks. And if I plot the data points for each of the students, and if I see some kind of a pattern like this, some kind of a linear pattern, I can definitely, confirm, or I can definitely get my notion validated that the external marks have a sort of relationship with my internal marks. Okay, so that is my scatter plot. I can do the scatter plot and figure that out. And we have already seen that, right? Now the question is, how do I decide on the straight line equation? Okay, or say, for example, this can be one option for a straight line. I can have this as an option for straight line. I can have this as an option for straight line. So which option for straight line should I have? I mean, which is going to be the closest to resemble the relation between the data? So what do we have to do that? For that, I have to figure out the value of A and the value of B. What is A? A is my intercept. And what is B? B is my slope, right? This is my slope. So I have to figure out the value of the intercept and the value of the slope, or the value of A and the value of B. Now, how do we do that? That is a very simple way to do that. And that is using a method called ordinary least squares, or OLS method. It is also called least squares method. Okay. So any one of you who have gone through some basic course in statistics, I'm sure you have gone through a chapter called curve fitting and method of least squares. So this is a part of that only. So we try to figure out a particular straight line, how it can be fitted to a data. So what is the way to do it? I mean, in a very simple term, you can simply use, to calculate B, you can simply use the covariance between X and Y and the variance of X. You can take a ratio of these two. Okay, and how can you calculate the covariance of X and Y? By simply using the statistical formula Xi minus X bar. X bar is basically the mean of Xi, and Yi minus Y bar. I mean, take a multiple of that for each of the instances, do a summation of that over all the instances, and divide it by Xi minus X bar, take a square of that and take a sum for all of the instances. Okay, that is the bar X. So Xi minus X bar square, a summation of that is my bar X. And for curve X, I take, for curve X, I need to calculate.
छोटी वाली ड्राइंग रूम में.
Okay. For the covariance between X and Y, we need to have Xi minus X bar and Yi minus Y bar, multiply that and calculate it. So for this particular data that we looked at, this particular data, 15, 23, 18, and 49, 63, 58. If you just look at the data, 15, 49, 23, 63, if we just look at them and take them as X and Y, so first of all, we can calculate the mean. So X bar is 19.9 and Y bar is how much? 56.8. Okay, so then I calculate the Xi minus X bar. For each of them, 15 minus 19.9, 23 minus 19.9. So each of them we calculate it. Same for Yi minus Y bar. So 49 minus 56.8, 7.8. So like this we calculate for all of them, and then we multiply them. So minus 44.93 into minus 7.8. We get plus 38.45. So we do a summation of that comes to 429.8. Okay, and then Xi minus X bar square. So Xi minus X bar is this one. So minus 0.493 square, almost close to 25, right? So 24.30. Like this, we calculate for all of them and calculate the sum of Xi minus X bar square. So this is my variance of X. Okay, so I get the covariance of X comma y, and I get the variance of x. Okay, and then I calculate the b, which is basically covariance of x comma y divided by variance of x. So what is the value coming as? 429.8 divided by 226.9. So that is coming as 1.89. Okay. Now, how do I calculate A? For A, I can just use y bar, which is the mean of y, minus b into x bar. So I can just use y bar, which is 56.8 minus b, so 1.89 into x bar, 19.93. So that is coming as 19.04. Now, what is going to be my equation? Y is equal to bx plus a. So what is b? 1.89. So the equation will be y is equal to 1.89 plus 19.04. So 1.89x into 19.04. This is going to be my equation. Y is equal to 19.04 plus 1.89x. Okay, this is my equation for the straight line. Okay, so this is how we derive the straight line equation for a simple linear regression. Now, when I go for a multilinear regression, say for example, the price of a property where you might have different predictors like the area, location, floor, aging, amenities, different predictors. And for each of them, we have a value. Then how do we do that? Same thing, we just have a change. Instead of 1bx, we will get b1x1 plus b2x2 plus, if there are n such terms, we will go till bn xn. Okay, so this is how we create the, this is how we fit a multiple linear regression curve. Okay, or a multiple linear regression model. Okay, so now we will again go to the Google Colab and we will see how to implement it. Okay, so I will implement it using a structured data. This is my example. So again, I import the Python libraries. Here we are using two scores, the mean squared error or the MSE and the R2 score. Okay, and same way I simply upload one more data set called the auto MPG data set. Okay, where I will predict. So this is my data set. Let me run the code. This is going to be a simple one. So let me run the code. Okay, let me also check whether the previous code has executed. Oh, I'm sorry, I clicked the wrong button. Okay, so simple linear regression. Now I again upload the auto MPG data set. Okay, so this is my auto MPG data set. This is getting loaded. And I will get the first few rows of the data set. This one has been started, so that's why we are not able to run the code for regression. So let me just try to stop it. Sorry, I have to interrupt the execution. Anyways, I think we need to look at the code from here. So now, when the segregated, the data holdout happens in the same way. I just split the data set into training and test in the same way. And then I apply the linear regression model. And the linear regression model, again, the way I feed the model is the same thing, predictors train, target train. And once the model is being fitted, I get the predictions using the predict function. And then once I get the predictions, I compare with the target, I compare with the ground truth. So target test gives me the ground truth. And the way I measure it now, I don't have the concept of accuracy because this is not classification. So for this, we do either a MSE or a R2 score. Okay, so both of them tries to find out the difference between the predicted and the actual value. The residual, remember yesterday we looked at it. So here we look at it and we get the mean scored error and the R2 score. So the mean score error is coming as 20.86 and the R2 score is coming as 0.63. So what is our target? We try to bring it down to as low as possible. Okay. And the way we can do it, we can either use certain techniques like we can either use the k-fold cross validation or the I can use multiple training data to kind of train the models and then ensemble it, or maybe I just check with different values of the training data and see how the the result comes out as. So like this, we can keep on improving the model. Okay. So this is how we can actually use the Python library functions to run the regression the regression model. Okay, simple regression model. Like this, you can also use the multi-linear regression model. Also, you can train the model and you can run it on a test data. Okay. So this is how we can do the whole thing. I will share this collab file with all of you. And any case, if you have any doubt in future also, this is my collab folder. That is this is the path of the collab that I am going to share. The collab the collab file. Okay, I'm going to share it with you in the PPT itself. And in case you have any doubt, you can always shoot a mail to my email ID. I will be happy to respond to you back. Okay. So I think that is all that I had to cover. In case there is any doubt or in case there is any question, I can now take it up.
Yes, sir.
Okay.
How decision tree works if all data values in dataset are numeric rather than categorical?
Okay, again, as I told, I mean, there are ways you can do it. Okay, like one simple way could be you can simply create categories out of the numerical value. You can assign different ranges of values, and for each range, you can assign a particular, what should I say, a particular tag to it. Okay, a name to it. Okay, so there are ways to do it.
How many maximum parameters are possible, sir?
For which one?
Just they have asked the question, how many maximum parameters are possible and how many maximum features are possible?
Features you can take as many as you want. I mean, all the predictors you can also use. But at the same time, as I told, some of the features, as you can see, I mean, just by looking at it, we can figure out that it's not important. Say, for example, name is not a feature which can help in any way in terms of prediction, right? Or at the same time, say, for example, roll number or something else. So again, certain aspects of feature selection like relevance or redundancy needs to be looked at. Okay, and based on that, if you want, you can always go on using the features, every feature, but it is always wise to take a subset of it which are most critical or most meaningful ones. Okay, and parameters, again, it will depend on the particular algorithm that we are using.
Yes, sir, they have specified it. It is for a decision tree.
Yeah, I mean, decision tree also, there can be standard parameters like, say, for example, how many levels we want, okay? How many maximum leaves we want. So all those things, what you can do is take your time and look at, say, for example, if you are going to go for an implementation in Python, just look at the sklearn online documentation, okay? And in the online documentation, you will see each and every classifier, whatever parameters are there, it has been very well described, along with, in case you do not give any value for that parameter, what will be the default value adopted? That is also given. Okay, so what I will suggest is you just take a look yourself. You will see that every information is there, either in the Python library, or if you use some other, say if you use R, you will also see in the R documentation, everything is there. Okay, so you can go to the respective documentation and fill it.
We have data set. We are splitting it into 70:30. Training the model using 70% of data, testing the model on remaining 30%, getting the result. Now please tell me, where is the research?
Where is the research? Okay, fine. So research can be in different dimensions actually. Okay, to name a few. Okay, so one area of research is you are applying it for a particular domain. Okay, so you, instead of coming up with an algorithm of your own, you simply apply it for a domain. Say for example, okay, I'm not using machine learning, but I'm using deep learning in a domain for say medical imaging. Okay, now in the medical imaging, I have images of different blood cells. Okay, taken from bone marrow. Okay, some of the cells, they belong to a specific category. Some other cells belong to a different category. Okay, now I am trying to train a model. How I am trying to train the model? Using the same set of things that you are doing here. Okay, but the difference lies where, see, again, using the code that you saw in the class today is not at all difficult. But the difficulty lies in the other things, like how better data you can get. How well are you able to massage the data? How well you are able to select the features, most important features. How well you are able to remove the outliers, the noises. How well you are able to train the or choose the hyperparameters. So the whole research lies in there. And while you are applying for a particular domain, like say for example, blood cell, okay, or another research area that I work in is in agriculture. Okay, so plants. Okay, so there also I have some training images and I have some test images. So the code that I use may pretty much look the same, but where the research will lie will be more in terms of getting the data, improving the data quality, choosing the subset of the data, all those things. Okay. There may be other research elements, and that is a more advanced element. Generally, the statisticians or mathematicians play a bigger role in that, where you come up with a completely new classification algorithm. So designing the classification algorithm or regression algorithm or whatever, designing the algorithm. Okay, so that is a completely different, it's more of a theoretical contribution. Okay, so that can also be a research area. So you don't use a decision tree. Use some own version of decision tree, which probably takes the essence of decision tree, but implements in a completely different mathematical way. Okay, I'm giving a very trivial example. It might not be so trivial. So distance measure for KNN, instead of using Euclidean distance, you use completely a different distance like a Mahalanobis distance. I'm just taking a very wild example. Okay. So that can also be a research area.
How to improve scores after model results?
Sorry, sir, your voice got a little distorted.
How to improve score after model results?
How to improve scores after model results? Is that the question?
Yes, sir.
Okay. So as I told you, I mean, in the last class also I covered, there are different techniques You can use ensemble techniques. You can use tuning some parameters or hyperparameters. In case it still doesn't give you good result, you can go for advanced models like neural networks. You can go for more advanced models. Say, for example, for images, you can go for convolutional neural networks. So that's how we have to go. I mean, even when we work, that's the way we work. I mean, by this time, we at least know that which kind of models need to be implemented for which kind of data. Okay, that notion we have got. Now, based on that, we can actually adopt that model and then keep on tuning the parameter. Okay.
Sir, I am confused with which algorithm for classification and which for regression. Or we can apply all algorithms for both type of problems.
No. When you are starting, you should adopt the models meant for classification as classification algorithms. Okay. So which are the ones? K nearest neighbor, naive Bayes, SVM, decision tree, random forest. And which are the problems related to classification? The problems, as I told in the last day, problems where the target variable is having a categorical data type. Okay. And regression problem where the target variable is of a continuous or a numerical data type. Okay. So there you apply the regression model. Okay. So at least to start with, I would suggest don't go for much of experiments. Okay. Once you are well versed with the models, then you can actually use classification models for regression or vice versa by using different techniques. You can do that. But for the time being, just restrict yourself for classification algorithms like naive Bayes, KNN, SVM, and all for the classification problems. Okay.
Yes, sir. Questions over, sir.
Okay. So I
Thank you.
Yeah, I had a bit of disturbance on my portion. I mean, suddenly I don't know why I was having some hiccups, uncontrollable hiccups. So that's
Okay,
why
sir.
I think it's got a bit of this thing. Flow got a little bit disturbed.
Thank you very much, sir.
Yeah, thank you very much. Thanks to all the participants for a patient participation.
Yes, sir. Thank you very much, sir, for enlightening our participants with the hands-on session and introducing our participants the Google Colab environment. And thank you very much, sir. You have taken good efforts, having hiccups. Thank you very much, sir.
Thank you.
Okay, sir.
Yeah.
I will share the feedback and I will.
And I will share the PPT right after this discussion is over. Okay, I'm going to send it out to you, and please share it with the participants. Okay.
Sure, sir. Thank you, sir. Thank you very much.
Okay. Thank you so much.